Hi everyone, our group number is 20 and our topic is experimental techniques to measure residual stress, and our team members are Banoth Bhadra, Tushar Narwade and Banoth Rohith, and we will provide our seminar link here. Let's come to introduction and problem statement. We will cover problem statement and motivation, and then scientific and working principle behind it, current status, and then challenges and future research trend. And as you can see in picture, there is a cracking in a cast aluminium ingot due to excessive residual stresses, and we have collected our source from this. So let's come to scientific basis and working principles. We have mentioned some sources of residual stress here, that are cold working techniques and phase changes. And what is residual stress? Residual stresses are internal stresses that remain in a material without external forces. And let's come to its main formation mechanisms. And first one is thermal gradients. Thermal gradients are non-uniform heating or cooling causing differential expansion or contraction. And second one is plastic deformation, and it is non-uniform mechanical processing like machining or short pinning. And third one is phase transformations. Phase transformations are volume changes during material phase changes. And residual stresses can be tensile or compressive, may exist at macro, micro or atomic levels. So now let's head to experimental techniques, and in this first one is X-ray diffraction. X-ray diffraction is in which we measure strain in crystal lattice through diffraction pattern shifts, and it's a non-destructive but limited to surface layers of depth less than 25 micrometers. And second one is Newton diffraction. In it we uses Newton beam penetration to measure bulk stress distribution through similar diffraction principles, and it's capable of depth measurements up to several centimeters. And third one is hole drilling method. It's a semi-destructive technique that measures strain relaxation around a drilled hole using strain gauges, and it's effective for near surface measurements up to 1 to 2 millimeters depth. And last one is contour method. It's a destructive method that cuts component in two and measures surface deformation to calculate stress map, and it provides complete 2D cross-sectional stress field visualization. And we have mentioned some more experimental techniques to measure residual stress, and like metallurgical testing and eddy current testing, and we have mentioned our source here, and it is. So now let's move to current status and applications. In applications of aerospace, we measure residual stresses in turbine blades, compressor discs, and landing gear components to optimize fatigue life. And in welding, we analyze stress fields in offshore structures, pressure vessels, and critical pipeline welds. And in additive manufacturing, we evaluate build induced stresses to minimize part distortion and optimize build parameters. In automotive, we use it in crankshaft fillet regions, wheel hubs, and critical chassis components for enhanced durability. We have prepared an table of comparison of residual stress measurement techniques. We have taken all the data from Google. And now let's move to X-ray diffraction. It has an accuracy of 20 to 30 megapascals and of penetration depth 5 to 50 micrometers, and its cost is like medium, and it's a non-destructive technique. And Newton diffraction has an accuracy of 30 to 50 megapascals and of penetration depth up to 50 millimeters, and it's a very expensive and non-destructive method. And hole drilling has an accuracy of 30 to 100 megapascals and of penetration depth 0.1 to 2 millimeters, and it's like affordable, and it's a semi-destructive method. And contour method has an accuracy of 30 megapascals and of penetration depth full section, and its cost is like X-ray diffraction like medium, and it's a destructive method.
So now let's see the challenges we faced in these experimental methods. So our first challenge is accuracy and calibration. As we have seen in the previous slide, there are different precisions and calibration standards for different experimental methods and different experimental setups. So this creates a first challenge, accuracy and calibration. Then next challenge is in XRD method, that is about the limited penetration depth as it has maximum 0.025 millimeter depth penetration. Then comes the next challenge about the cost and infrastructure challenge in neutron diffraction method. There are hardly 30 specialized facilities worldwide of neutron diffraction method. So this is very complex too, and which makes it very costly. Then our next is destructive aspects. Then this mainly happens in hole drilling method and contour method due to its destructive nature, which also destroys the sample integrity and limiting the repeat measurements. As you can see in picture, the sample is bit damaged due to the hole drilling method. The source we have taken this picture is mentioned here, as you can see. Then our final challenge is interpretation complexity, which creates challenge in analyzing stress gradients, plastic anisotropy, and heterogeneous materials, which is bit complex to study. So now let's head to the future research trends. So in this, our main idea revolves around the AIML model. As you can see in the picture, there is a decision tree and original data set through which we are predicting and making a model of the sample and predicting the where actually is residual stress acting. So we are precise up to 10% absolute percentage error. This mainly addresses the problem of accuracy, and also it's portable, low cost, and ideal for industrial applications. So this solves mainly most of the challenges we have covered in the previous slides. So now let's conclude with references and acknowledgement. In this slide we have mentioned the sources of the pictures we have used in our slides. By clicking on the link, you can reach to the pictures and see our references. We thank Professor Pradeep Dixit for guidance, and thank you for watching our seminar.